This program was brought to you by Coller Institute of Venture at Tel Aviv University.
So my presentation is an engineering presentation, so I'm going to talk to you about the work that we've been doing at that we've been doing at the Institute of Systems and Robotics on underwater robotics. Actually, I'm mostly a communications guy, so most of what I'm going to show you today is the work of my colleague Antonio Pascual and his dynamic systems and ocean robotics team at the Institute for Systems and Robotics. So this will be a very, very short presentation, so there's almost no outline. So I'll start just by giving you the briefest overview of the history of the group, and then I'll showcase two projects, one of them ongoing, the Morph project for marine habitat mapping, and then I'll go on to Why Must, a European project on geophysical surveying that is about to start next month. So the activities of our underwater robotics group, they started in the 1990s with the first participation in a European project where we helped develop an underwater vehicle. So at the time this was a monolithic vehicle, big beast, very hard to deploy in the water and retrieve. So over time, over several European projects, we learned how to build various systems that are needed to create underwater robots. And so lately, as of 10 years ago, we went into the field of collaborative robotics. So having teams of robots carry out missions more efficiently than a single robot could. And so what I'm going to show you today is in this line of work on collaborative robotics. So the first project is Morph, the marine robotic system of self-organizing, logically linked physical nodes. So this has the thrust for this is provided by our colleagues of IMAR in the Azores. So the challenge that they posed to us is to map complex habitats, complex underwater habitats. In particular, they were interested in cliffs and other structures that are very hard to survey with current technology, including cliffs with negative slope. So it just goes this way and you have to survey underneath. So how do the humans do this? Well, they use the technique of hugging the cliff. So they stay close to the surface of the cliff, regardless of whether it's a negative slope or not, and they take note of the communities, the animals, the plants that they see in the cliff. Of course, this is very time-consuming, so the challenge is to develop technology that enables us to do something similar with robots. So when to survey this type of habitat, they need several types of data: high-resolution digital terrain map, imagery, detailed imagery of the structure, acoustic maps, 3D maps, various types of data. So the proposed solution for this is to deploy what we call a super vehicle. So this is a set of underwater vehicles, but they are operating in close coordination among them. So they act as one, although they are several vehicles and they are not physically linked. So this is the concept of the Morph super vehicle. So the idea is the super vehicle conducts some sort of survey. For example, here it has a surface support chip. At some point, the whole set approaches the cliff here, and then the formation, it shifts from the bottom survey, it shifts into, this case, the vertical survey. Continues the mission. At some other point, it reaches the point in the cliff with negative slope, and again it changes its shape to continue doing the mission. This is something that you cannot do with a monolithic vehicle. Technology just doesn't allow you to do this. So to materialize this vision, there are a number of technical challenges. From the planning, navigation, communications, many different things. I'm not going to touch upon most of them in this presentation. This vision is being materialized by a big consortium with several European countries plus people from the United States. They bring into the consortium a number of different vehicles. You see them here. A number of experimental facilities. You see them here. So it's a very ambitious goal of building a team of robots from various from the various partners, heterogeneous team of robots, and making them do useful work. So regarding control, this is one of the strong topics that our institute is addressing. So the goal is how to make the robots maneuver cooperatively. And this is to be executed even in the case where you have shaky communication links, which is something that is inescapable in the ocean. So you might not know this, but to communicate in the ocean, you have to do this acoustically, and acoustics is tricky. So even in the best of situations, your acoustic communication links are going to fail every now and then, relatively often actually, and so you have to plan for this. So the concept is that they are developing is range-only formation. So the idea here is that you have a leader vehicle, this one, and you have two follower vehicles. So the goal is to design control strategies for the followers. Actually, this picture here shows two leaders. So how to design control strategies such that the follower that is measuring its range to each of the two leaders can navigate so as to keep, in this case, the distance to the two leaders constant, meaning that it keeps its place in the formation. So this has been developed and field testing. I'm going to show you results for a test site that was conducted here in Lisbon at the Expo 98 Marina. So what you will see here is similar to the previous slide. You will see two leader vehicles. Actually, you only see the results. So you have two leader vehicles. This one and this one. They're executing a figure of 8. They are two surface vehicles. And then you have this vehicle here, which is a follower. It's measuring the range, and as you see, it nicely follows the leaders into the figure of 8. To make this happen, there's a key component, as I said, which is the acoustic communications and positioning. So this is the part that I'm mostly involved in. In the framework of Morph project, the acoustic communication system is also an integral part of the system that allows you to measure ranges between the vehicles in the formation and allows you to keep the formation. So I'll show you this video about some tests that we conducted in the Azores this summer. So this is, oops. So it's more sophisticated than the 3-vehicle test that I showed you in the marina. So in this case, this is an actual sea test, not in the port, not in the marina. And there are 6 vehicles involved. This is a very short video, just 2 minutes. So you will see 3 vehicles from IST. These are the Medusa vehicles. Then you have other underwater vehicles from Italy, from Germany, and from Spain. So this is the kind of formation that we have. And this, we believe, is our key contribution to this European project. You don't see, currently, you don't see underwater formations of vehicles with 6 heterogeneous vehicles as we have demonstrated here. So this is a unique capability. So the maneuver that you're going to see here is very simple. So it's just a linear survey and then going into an arc. So this one here in the foreground is one of the Medusas from IST. In the background, you have one from Atlas Electronic in Germany. So they are all navigating here with a similar scheme to what I showed. So they are measuring ranges to each other, and then you will see here actually this one avoiding a virtual obstacle that we put in its path. So it's a fake object. We just tweaked the measurements from its sonar system so that it thinks it has something in front of it and it deviates. So the second project that I will tell you very briefly about is WIMAST, a project on geophysical surveying. So the goal is to improve upon current geophysicals and underwater geophysical survey systems. Again, a team of many partners from various European countries. So the application scenario here, well, in this slide I show you what current geophysical survey systems do. So you have this ship that is carrying an acoustic source. The sound insonifies, travels through the water column, penetrates the bottom, gets reflected by the layers in the bottom, and is picked up by these lines of hydrophones that are being towed at the surface. So by looking at the pattern of echoes, you can figure out the structure of the bottom. This is very cumbersome. Because these lines can be very, very long, like 5 or 6 kilometers. They get tangled in each other. The whole system is very, very hard to maneuver. And so you really want something that is more easier to deploy and to steer. So the WIMAST concept, in its easy scenario, simply replaces the long lines at the surface by shorter lines of hydrophones that are being towed by teams of autonomous surface vehicles. So this makes it much easier to deploy and to steer, but we are aiming for a harder scenario, this one here, where instead of having the vehicles at the surface, you have them near the bottom. So what's the advantage of this? Is that when the sound gets reflected on the layers, various geological layers in the bottom, it doesn't have to travel through the whole water column, which introduces a so-called blurring effect. And so you get potentially a cleaner picture of what the structure of the bottom is. The challenge is that, unlike in the easy scenario where you can have GPS to guide to position your vehicles, here you're stuck with acoustics and in pairwise range measurements, as I showed you in Morph. But the results that we already have in our hand for Morph embolden us to believe that we can make this work. Okay, so there are a number of technical challenges here regarding communications and networking. As I said, acoustics is tricky, and it takes, to measure acoustic range, it takes something on the order of a second or half a second. And so when you have many AUVs in the water and you are systematically measuring ranges between pairs of vehicles, very soon you find out that there's not enough time for you to do all the measurements. So doing this in a time-effective way is needed. There are other challenges: precise navigation, criteria for adapting the shape of this formation. Now we have something that current geophysical systems do not have. They have this fixed linear shape, whereas we can shape our receiving array of hydrophones in very flexible ways. So we have to come up with criteria to adapt the shape, to determine what's the good shape and how to get there. And then, of course, there are the acoustic tomographic techniques that will enable us to actually take these measurements and determine the structure of the body, of the bottom. And that's the topic of the next presentation by Paulo.
This program was brought to you by Coller Institute of Venture at Tel Aviv University.